All right, fantastic. Thank you. Thank you for the invitation and thank you everyone for showing up. Hopefully the online people can hear and see and so on, but let us know if there's any problems. So yeah, I'm going to talk about this grandly titled Breaking the Entanglement Barrier. Before we get on to the physics, I'm going to start with a little advert. So you asked me what's the Unitary Fund doing here? A couple of years ago, I was involved in a podcast project where we were interviewing a bunch of people from all different areas in quantum technologies about their life, their career, their work, and so on. So if anyone's interested in hearing from all these people, please do check it out. You can find it on all the major podcast platforms. We're considering keeping this up and doing another series. So yeah, if anyone likes it, do let us know. I think that's all I had to say about that. So customary advert done. Now we can get on with the physics. So my background is that I'm a condensed matter physicist by training. I started off doing very much pen and paper, kind of real traditional condensed matter physics, gradually went more and more numerical, eventually ended up working in industry for a little while in quantum computing, and now I've started a research group in Edinburgh. But the main thing I'm interested in, despite the quantum computing flirtation, the main thing I'm interested in is still condensed matter. It's still this idea of what happens when I put large numbers of interacting particles together. What kinds of interesting things can they do that individual particles might not do themselves? And the main thing that I've been interested in for a very long time is this question of thermalization. What does it mean for a quantum system to thermalize? How do they thermalize? When do they thermalize? Particularly, when do they not? So this might be familiar to a lot of you in the audience, but the example that I normally give is this example of coffee with milk. If you prepare this system in some structured initial state on the left, you allow it to evolve in time, the coffee and the milk get mixed, and eventually you end up with some featureless thermal equilibrium state. So the information, if you like, about the structure of the initial configuration gets lost. So you can say that thermalization is essentially the loss of information. I'm being a little bit hand wavy here because, of course, everything in that little glass is everything that started in the glass is still in the glass. So it gets kind of jumbled up enough that you can't really retrieve any information about the initial state, not in any meaningful way. So very loosely speaking, thermalization is the loss of information. And if we want to design quantum technologies that rely on being able to store or retrieve or manipulate quantum information, really, we probably want to at least understand thermalization, if not outright prevent it. So that's the kind of the big picture goal. That's the thing that I've been interested in looking into for many, many years now. Now, in quantum physics, I guess we have a standard set of tools. So this slide is a bit of an introduction to the notation that I use. Hopefully this will be fairly familiar to most people. But in most of what we do in quantum physics, at least for closed quantum systems, we start from some Hamiltonian. And in this talk, I think all the Hamiltonians I'll use will be fermionic. They'll look something like this. So my notation is I'm using C and C dagger for the fermionic creation and annihilation operators. This is a non-interacting fermion Hamiltonian, and in most of what we'll talk about here, we'll be looking at disordered or quasi-disordered Hamiltonians. What that means is this unsightly potential here will be some type of random number, and then we've got some kind of nearest neighbor hopping. This is a 1D Hamiltonian. So given a Hamiltonian, if we want to compute anything about it, the sort of the holy grail in at least numerical condensed matter would be we want to build this Hamiltonian as a big matrix. You diagonalize the matrix, and then at that point, problem solved. You can compute anything you want, right? We've solved the problem. We can compute whatever quantity we want. We've got all the information about it. This is what we do in an ideal perfect world. Of course, the world is not entirely perfect, and trying to do this is a bit of a losing game. These Hamiltonians, at least for interacting systems, for interesting systems, they're exponentially large in the system size. They take up a huge amount of computer memory, and playing this brute force game doesn't get you very, very far. I believe the largest exact simulations that you can do with Archer 2 in Edinburgh, the UK's largest supercomputer, I believe you can simulate up to 44 fermions on that thing. That uses the entire system. That's about 750,000 nodes, and I have no idea how much memory, but it's a lot. So 44 particles is not really enough to say much about, deep physics about collective behavior. So what else is there? So the main thing you could start with is, I guess, what I just mentioned, exact diagonalization. You can build the Hamiltonian as a big matrix. You can diagonalize it. Great. That is exact, as the name suggests. But as we just mentioned, the computational cost is huge. So realistically, above a few tens of particles, we can't do anything fully, completely, exactly. So what other methods do we have? Tensor networks, I imagine, are familiar to most people here. So tensor networks are the other tool that we fall back on, at least in one dimension quite often. They work really well for reasons that I'll not get into, because I imagine most people have heard of them. They're fantastic if you have weak entanglement, if you're in 1D, if you have a gap system. They're less good if you have long-range interactions, if you have volume law entanglement, or if you're in 2 dimensions or higher. Not to say you can't use them, but it's certainly much, much more of a challenge. So if you want to look at 2D systems, or you want to look at time evolution to very long times where the entanglement eventually grows to be significant, tensor networks are not maybe the most efficient way of doing it. Other techniques are things like quantum Monte Carlo, which seems a lot less fashionable these days. People don't talk about Monte Carlo very often, but it's still a pretty powerful technique. It's great for equilibrium. It's great for ground states. It works in 2 dimensions as well, which is pretty good. Fermion sign problem notwithstanding. But Monte Carlo is not really as great for dynamics. It's not so great for excited states, so it still has some limitations. And then there's other things, stuff like DMFT, just as an honorary mention here. Things like DMFT work really well in the high dimensional limit, but not so well for low dimensional systems. I've not mentioned neural quantum states in here because I don't understand them, but they seem super interesting as another alternative. But there's kind of a picture being built up here where we have a variety of different techniques that can all do slightly different things. And they all fall down in other areas. So let's say if you wanted to compute the long-time dynamics of a 2-dimensional quantum system, that's something that really interests me. And that's something that none of these techniques on the screen are capable of doing in an efficient or general way. So what I would like to do is figure out a technique that allows me to look at long-time dynamics of 2D systems so that I can start to ask interesting questions about thermalization. Now, normally the structure of a talk is you'll come to some sort of simple example, and then we'll kind of build up the building blocks bit by bit, and then we'll get to the end. What I'm going to do here is flip that completely on its head, and I want to show you the result that we are building towards. Now, you will not understand everything that appears on this slide yet. We're going to spend the next 45 minutes building back up to it. But what I want to say is that of all the techniques here, nothing here can handle the long-time dynamics of large 2D systems. The technique I'm going to tell you about can. What you're looking at here are a bunch of plots of infinite temperature correlation functions. We'll get to what that means later, for 100 fermions in 1D and in 2D. So in 1D, it's a chain of 100 fermions. In 2D, it's a 10 by 10 grid. You're looking at the non-equilibrium dynamics, and the hopping axis here, sorry, the time axis here goes up to 10 to the 5 hopping times. That's way beyond what you can do with other methods. So if you imagine doing tensor network simulations, you have some, Trotter time step that's like 0.1 or 0.01. That would be a lot of Trotter time steps to try to get to a time this long. So the method that I'm going to tell you about allows us to compute long-time dynamics, very long-time dynamics of 1D systems in the top row, 2D systems in the bottom row. So this is what we're aiming for in the next 45 minutes. This is why I'm here. This is why I'm taking up your time this afternoon. This is what I'm going to tell you how to do. The logic behind this comes right back to the initial slide that I showed you when I said, given a Hamiltonian, what do we want to do with it? We want to diagonalize it. Great. So let's say we don't know how to build this thing as a big matrix in computer memory. Let's say I give you some analytical expression for a Hamiltonian, and we want to diagonalize it. How might we do that? So the Hamiltonian, we'll split it into 2 terms first. We'll call it H0, which is the diagonal part, and V, which is the off-diagonal part. And so, I literally mean if you build this as a matrix, H0 is just the diagonal, V is everything else. What we want to do is transform the Hamiltonian such that it becomes entirely diagonal. And the way that I was taught to do this, at least in my final year of undergrad or first year PhD, was to use a unitary transform. So the sort of schematic visual that I like to use for unitary transforms is you start from a Hamiltonian that is in some structured initial state that is maybe not in its simplest possible form. And a unitary transform is just a rotation, right? It's a basis change. Rotations in 3D space are unitary transforms. All we want to do is make this rotation, move things around in the Hamiltonian to get it into its simplest form, its diagonal form. And kind of crucially, part of the reason I like this image is that unitary transforms don't add or remove information. So it's not like doing DMRG or something like that. There's no decimation involved. You're just moving the information around from the original difficult configuration into the final simpler configuration. So that's the game. Can we find a unitary transform to diagonalize our Hamiltonian? The way that I was taught to do this in my undergrad was a thing called a Schrieffer-Wolff transform. Anyone heard of Schrieffer-Wolff's? A few nods? Cool. Okay, so let me just, again, establish some notation and explain what the Schrieffer-Wolff is. So if we start with some Hamiltonian H, we want to make a unitary transform of this Hamiltonian. The transformed Hamiltonian will be H tilde, and the unitary itself is this e to the power s. S is some generator, which we're not going to specify at the moment. So the unitary is e to the power s. In this form, it's not super informative. What you can do is you can Taylor expand this exponential into powers of s. You can then plug that expression back into the top line, and you get this kind of a mess. You can see how you can do this. You can keep expanding these exponentials to higher and higher orders, get a longer and longer expression. But if you kind of bundle it all together, if you spot some simplifications, what you find is the end result is the transformed Hamiltonian, at least the leading order in S, is the original Hamiltonian plus some commutator. It's commutator of S with H. So the game is, if you can find some generator such that this commutator subtracts off the off-diagonal bit of your Hamiltonian, you can approximately diagonalize it. Is everyone with me so far? Cool. So if you can find a generator, S, which is not easy, if you can find one that satisfies this, you can approximately diagonalize your Hamiltonian. But there is this ... term here that will cause problems and make your life miserable. This ... thing is not necessarily diagonal, it's not necessarily small. If we can argue the ... can be neglected, great, you can diagonalize your Hamiltonian. But in general, for most interesting problems, you can't. So this complicates things, and Schrieffer-Wolff is nice in some examples, but it's not a general tool that will always work. The main idea behind the method I want to talk to you about today is, instead of trying to diagonalize the Hamiltonian with one big unitary transform, one big approximate transform, what I want to do instead is apply infinitely many, infinitely small transforms. So let me explain what I mean by that. And this is the method called continuous unitary transforms, or flow equations. So what I want to do is introduce a fictitious timescale called the flow time, which we labeled L. The Hamiltonian at L equals 0 is the original Hamiltonian, whatever that is for your problem. And then what we're going to do is continuously evolve this Hamiltonian in flow time, such that in the limit of L to infinity, the Hamiltonian is diagonal. So in the diagonal basis, I call it H tilde. The tilde will always be diagonal basis. So how do we do this? Well, the building block is essentially the same as the Schrieffer-Wolff that I just showed you. We apply some unitary transform to transform the Hamiltonian from a time step L to a time step L plus dl. The unitary looks a lot like the thing on the previous slide. Instead of e to the s, here it's e to the power of some generator eta multiplied by dl. dl is an infinitesimal. So you can Taylor expand these exponentials again. You can run through all the same steps as on the previous slide. And what you find is that the evolved Hamiltonian is the old one plus this commutator with no high order terms. Now that's the difference. The high order terms would all have powers of dl squared or greater. If dl is really infinitesimal, they're 0. They can be neglected. This is exact. So we can exactly evolve the Hamiltonian by some infinitesimal time step. If we can do that once, we can do that infinitely many times. So we can go from L equals 0 all the way to L equals infinity and diagonalize the Hamiltonian. And in practice, rather than doing this kind of iteratively, what you can actually do is just move some things around in that equation, and you get this equation of motion for the Hamiltonian, the flow equation for the Hamiltonian. Okay, so dH by dl is equal to this commutator. It looks a bit like Heisenberg evolution, if you think about it, except instead of evolving a state with the Hamiltonian, here we're evolving the Hamiltonian itself with some generator eta, which again, I haven't told you what eta is just yet. There are various different choices that you can make. We'll get into that on the next slide. Everybody with me so far? Okay, so the game is, we're going to do infinitely many, infinitely small unitary transforms. What we want to do is compute this flow equation, this differential equation at the bottom, and we want to solve it. And it looks fairly simple in this form. It's just a commutator. So let me walk you through an example where we can actually apply this completely exactly and get a little bit of intuition about how this works. So we'll start from the Hamiltonian that I showed you earlier. So this Hamiltonian describes non-interacting spinless fermions here in one dimension, nearest neighbor hopping, and we'll have some disordered potential. So that first term with the HI in it, that'll be a disordered random variable. For reasons that will become apparent, I actually want to write the Hamiltonian in a slightly more general way. So instead of allowing for just nearest neighbor hopping, I want to allow for complete long range hopping. So I've changed a couple things from the previous slide. Now the second term, the hopping term, has just arbitrary indices I and j. I'm allowing for long range hops. And the coefficients here, h and j, now have picked up an L dependence. So the idea is that we start from the original Hamiltonian at L equals 0, and as we move towards L equals infinity, these jij terms should go to 0, and the h's will do something else. They'll go to the eigenvalues of the problem. So here, the diagonal part is h0, that's the first term. The off-diagonal part, v, is the second term. The generator that we'll use for this transform will be the commutator of h0 with v, the commutator of the first bit of the Hamiltonian with the second bit. There are various deep reasons why this works. So this generator was discovered independently, I think, at least 3 times. Mathematicians found it as some particular solution of a gradient descent problem. I think high energy physicists found it through some link with renormalization group. I have no idea how condensed matter physicists found it. I think possibly just because it worked. So they found it in several different ways. You can get really into the math about why it works, but instead of trying to justify that, what I'd like to do is just show you that it does, in fact, work. This generator does diagonalize the Hamiltonian.
You mean for bilinear?
In general, for all Hamiltonians, but we'll get onto the interacting case in a bit. So let me show you how it works for this one first. The mathematicians, by the way, they call this double bracket flow rather than flow equations. It has some slightly different names in the literature. The reason for that is that the differential equation is the commutator of eta with h. Eta is itself a commutator, so if you plug that in, you're solving this kind of double commutator. So this is the double bracket flow that mathematicians speak of. I believe the mathematician who discovered this was called Brockett, and my old boss, Jens Isert, finds it hilarious to call it double Brockett flow. So there you go. But the game here is we want to compute these 2 nested commutators to compute this equation of motion for the Hamiltonian. Now you can do this, it's a couple of lines long. I'll skip the details and I'll just show you the answer. Everything is completely closed. There's no approximations. The answer looks something like this. Now, I'm not expecting you to look at this and gain any particular insight from it. I just want to put this up to say, this is a relatively compact expression. This is exact, and it does at least fit on one line on the board. So this doesn't look too intimidating, I hope. It's a relatively simple calculation that takes a few lines. What's slightly more meaningful is instead of saying, let's look at the flow of the entire Hamiltonian, you can actually break this down into individual flow equations for the coupling coefficients in the top line, for the HI and the J, essentially just by matching up the terms in the top line with the terms in the bottom line. What that gives us are a set of coupled differential equations for all of these variables in the Hamiltonian. What we want, what we hope, is that in the limit of L to infinity, these J terms will get smaller and smaller and will vanish. And if you look at the first term of the dJ by dL equation, that's what they do, right? You have a minus J times something positive. So that means that these J's will decay as L increases. The second term here, that does something else. Let me say it's usually small, and I'll justify that in a second. If we forget the second term in that equation, you could solve the dJ by dL equation and say these J's will decay exponentially as L increases, which is really nice. That's what we want. And then the dH by dL equation, essentially that's bookkeeping. That's just keeping the transform unitary. That's just transforming the J's in the correct corresponding way. So we could kind of look into this and talk through all the terms in these equations and blah, blah, blah. I don't think that's a useful thing to do. What I actually prefer to do is say, let's just watch this method in action. So this is a Hamiltonian. This is the previous Hamiltonian built as a matrix. So you have a disordered potential down the middle diagonal, and then on the what I'm told are called the sub and super diagonals, you have some uniform nearest neighbor hopping on either side. Now, what I'm going to do is I'm going to play you a movie of how this Hamiltonian evolves under this continuous unitary transform. What we hope is that we start from this, and then as the movie goes on, the Hamiltonian should get more and more diagonal. And if we get a diagonal Hamiltonian, then success. So the first thing you'll see when I play the movie is it is a complete disaster. It does exactly the wrong thing. The Hamiltonian does not become diagonal. In fact, it becomes very, very dense, and you have hopping terms all over the place, which is why I made the Hamiltonian allow for long-range hops. But you can see that the longer we wait, the closer it gets to diagonal. So ultimately, this does work. That's the main takeaway one from this. It does work. It does diagonalize the Hamiltonian. The downside is, as you saw, it does not preserve the sparsity of the Hamiltonian. So it generates all possible off-diagonal terms in the intermediate stages before it sends them all to zero. And then you can see also, all these off-diagonal terms, they don't all go to zero at the same rate. Some go faster than others. So there's a kind of a hierarchy of timescales in here. So we kind of asymptotically approach a diagonal Hamiltonian. The longer you're prepared to wait, the more diagonal it gets. Ultimately, at some point, you just cut it off and say it's close enough. You know, if the off-diagonal parts are smaller than 10 to the minus 6 or something, it's close enough. So this is how the procedure works for non-interacting systems. And we're going to dig into more complicated bits in a second. So this is a good point if anyone has any questions or if anything I've said isn't clear. Yes.
Like, what should we think of as like the physical meaning of these, like slowest decaying off diagonal?
So the physical meaning actually comes from, if we look back at the equations governing this flow, you can see that the decay of the j's, right? The first term here is proportional to the difference hi minus hj. So if that difference is big, then these off-diagonal terms will decay rapidly. If that difference is small, then they decay much more slowly.
Almost resonant eigenvalue.
Exactly, right? So that's the reason why there is this hierarchy of different timescales that appear. Okay. Any other questions? Okay, so so if you have a lot of closely spaced diagonal terms, then you will require a much longer flow time to diagonalize it. I think if you have I would have phrased it differently. I would have said if in a strongly disordered system, they're more likely to be different to each other. But yeah, you will run into problems where you will end up with pairs that are very similar to each other. And in fact, that brings me on to the next slide, because you might guess from this that actually, if the disorder is weak, and in the limit where there is no disorder and all the h's are identical to each other, there's a real problem here in that both of these equations are zero. So for a completely translationally variant system, then the flow of the Hamiltonian, given by this, is zero. Nothing happens. This is a consequence of the generator that we picked. So this Wegener type generator, it works by getting rid of what it calls high energy off diagonal terms first, and progressively works towards lower energy off diagonal terms. If all the off diagonal terms are, let's say, equal in energy, it doesn't know where to start. It's kind of like an unstable fixed point in your normalization group. If you're exactly at that fixed point, the method doesn't have a place to begin, so it can't do anything at all. Now, there's a couple of ways that you can get around this. So what you could imagine doing is just adding in some weak randomness. That's like saying you're perched at this unstable fixed point. You just want to perturb away from it just enough to give the method a place to start. What that will do is the bigger the randomness you add, the more you modify the eigenvalues. But the less randomness you add, the longer it will take to converge. So that's a bit of a compromise. You can also just Fourier transform the whole thing, which is what people did originally when they worked with this. So in the kind of mid to late 90s, when people started to discover this method, mostly what they would do is Fourier transform it, do the whole thing in momentum space where this issue doesn't arise. But I want to do this in real space, so this one's a bit of a problem for me. And it was a problem when we originally started this work, and it remained that way for quite some time. So the question is, can we do better? Can we find some other way to transform the Hamiltonian such that it doesn't completely fail for clean systems? Ultimately, the reason that we get this behavior comes from the choice of generator. You can obviously choose a different generator. In the entirety of the literature for this stuff, there are, I believe, 3 named generators. The one we've used here, Wegener, is the one that numerically is the most well-behaved. There are other ones that work for clean systems, but they're nightmares. They have highly oscillatory terms and all sorts of other things. So really what we want to do is take this Wegener generator and try and patch it up. So the way we do that, if we come back to this picture that I gave you at the beginning, the procedure is you start from a Hamiltonian, it has some structure in it, and you want to make a rotation into the simple form. The problem is if you have too much structure, if it's a completely clean system, the method doesn't know where to start. But this transform is a unitary transform, right? Unitary transforms preserve all the eigenvalues, blah, blah, blah. There's no reason that I have to just make one unitary transform. I can make 2 successive unitary transforms in a way that kind of scrambles it. So this was the little kind of breakthrough we had that made this method much, much more practical. So instead of making 1 unitary transform, we do 2. We make what we call a scrambling transform first, which just kind of messes up the structure of the original Hamiltonian. So if you have too much structure, what this does is it kind of just messes the structure up, gets rid of it essentially, adds some kind of effective disorder, let's call it, and then we can apply this Wegener generator I showed you on the previous slide, and now it knows where to start. So we can always do this. You can daisy chain different unitaries with different properties. Essentially, whenever you run into a problem with this method, that the particular unitary you want to use doesn't work for some reason, well, then you look for a different one, you apply that one first, and there you go. And because these are all unitary, you're always allowed to do this. Every unitary transform preserves the eigenvalues. You're always allowed to do this. In theory, you can make a completely random unitary transform first. In practice, you can usually do a little bit better, but any unitary is a valid one here. And then just to show you an example of this in action, what you're looking at in these plots is the flow of all the coupling constants in the Hamiltonian. So these are very small systems. The solid lines are the flow of the diagonal elements. The dashed lines are the flow of the off-diagonal elements. They should all go to 0 as L increases. The black dashed lines are the eigenvalues. I appreciate there's a lot of lines on these plots, but in the right-hand column, what you have is the generator I just showed you applied to a strongly disordered system at the top. And what you see is everything is nice and smooth, everything is very well, and all the diagonal elements do flow to the correct eigenvalues. In the bottom line, you see that generator applied to a totally translation invariant system, and you see it doesn't do anything. It's a complete failure. On the left-hand side, you have what I've labeled the adaptive generator. That's basically this scrambling transform first. In the top line, it works just as well as the Wegener one. It has some small differences, but it works. And the bottom line, applied to the clean system, you can see it works really, really well. And then the dashed gray lines in the bottom panel are where we hand back over to the Wegener generator. So this combination of generators works. It allows us to diagonalize clean Hamiltonians, disordered Hamiltonians, anything we like. Great. And all we have to do is compute a couple of commutators. So problem solved? Not really. So they were non-interacting systems. So non-interacting systems, we already know how to solve them. So this method is complete overkill for those. But it's nice that we can show that it all works exactly. If we start looking at interacting systems, then things are a bit more complicated. So now we take a Hamiltonian, effectively the same as the one we had a minute ago, but we add a density-density nearest neighbor interaction at the end here. Now this complicates things a bit. You can play the same game. You can define the middle term here to be the off-diagonal part. You can compute the generator as the commutator of that bit with the rest. You can compute the flow equation. And what you find is that the Hamiltonian no longer remains closed. So you can write it in the diagonal basis. Diagonal to me means that you can write it in terms of number operators, right? All these number operators are all mutually commuting. So this to me is what I'm calling a diagonal Hamiltonian. You can write it in this diagonal form, but the cost is now you generate this new 3-body interaction term that wasn't in the original. Okay, and these IJKs, these can be anything. So this is not like a nearest neighbor, like a little cluster of interacting particles. These can be long-range interactions across the entire system. And again, there's a ... hiding here. There'll be a 4th-order term, 5th-order term, and so on. So this is the price you pay. You can't kind of hide the exponential complexity under the rug here. It always comes back somewhere. So for interacting systems, we can't keep track of all of these couplings if we want to look at large systems. So what we have to do is at some point say enough is enough. We'll get rid of the terms above a certain order. Loosely speaking, the higher order terms all come with prefactors that are powers of the microscopic interaction strength. So if the microscopic interaction is 0, this third order term never appears, the second order term never appears. If the interaction is relatively weak, these higher order terms get weaker and weaker and they can be neglected. You can make this precise, you can put proper error bounds on this, and you can compute norms and so on and keep track of what type of error is generated here. So for the time being, let's just say we'll work with relatively weak interactions where this is possible, but we can get more into the details about when is it possible later. Now, if you try and play the same game we did earlier, if you try and work out the flow equations for the Hamiltonian, you can do it. I'm going to show you analytically what they look like. Don't panic. There's not a lot of physics in here. All I want to say is you can do it. They're much more complicated. This doesn't fit in a single line anymore. It takes the whole screen. It's much more complicated, and this is for the crudest possible approximation. This is only allowing for a very, very tiny fraction of newly generated terms. You might think that's not so bad. If I tell you that it involves applying this identity 6 times, you might start to understand why actually this is not practical in any way. And it certainly isn't practical to go to higher orders to include these higher order correction terms and so on. This is where we got to probably about 8 years ago with the method. I did this calculation once when I was a postdoc, and I told my boss I never wanted to do another commutator again. And at that point, we kind of thought that's probably as far as we can go, because the complexity was just mounting up. It's taking a long time to compute the higher order terms. It was difficult to solve them. You have this huge set of coupled differential equations, and it's very easy to make mistakes in this because, as you can see, it's pretty complicated. I'll tell you for free that there is one mistake in this giant identity that's appeared in white, but good luck finding it. How do I know there's a mistake in there? Well, because a couple of years later, we came back to this method and we found a much better way of doing it. So after we tried doing it this way, I gave up. I went and did a different postdoc. I learned about tensor networks. And then I started to realize that actually we can automate this whole process. We don't need to do the entire thing by hand. Now, this is the new version, the version that actually works and is actually practical. So what I want to do is introduce you to my Hamiltonian. So here I've written an interacting fermion Hamiltonian in the most general way I can think of writing it. We have a quadratic part, this C dagger ICJ, and a quartic part where I'm allowing all 4 of these operators to be on different lattice sites, potentially. So this covers all the sort of standard cases, your non-interacting spinless fermions. You can cover quite a lot of different Hamiltonians with this general way of writing it. The colon signs, by the way, they mean normal ordering. We're not going to get too much into what that is. It's a technical detail. It is important. You can ask me later if you want to know what it means. But the point here is my fermion Hamiltonian looks like this. I have one term in it that has 2 operators, 2 free indices, one term that has 4 operators, 4 free indices. Let's take that seriously. And let's say the term with 2 operators, 2 indices, well, that's a matrix. The term with 4, that's a tensor. A rank 4 tensor or an order 4 tensor, whichever you want to call it. And at least computationally, that's how I want to store this Hamiltonian. Okay, matrix plus a tensor. Okay, so far, so good, so what? Why does this help? It helps because all these commutators that I want to compute, all these really big lengthy identities I showed you a second ago, they're actually just the sum of tensor contractions, or I kind of vary between calling these 1-point or 2-point contractions. I guess here I'm calling them 1 point. So it's just the sum of these contractions. So this expression written here is on the left, the commutator of 2 matrices, H and V, written out in elements. And on the right, the same thing written in terms of this graphical notation. So all I'm doing is I'm saying how many different ways can I connect an up arrow from one of these objects to a down arrow from the other, and I'm summing all the terms. So the up and down arrows in the top here, they refer to creation and annihilation operators. So that's matrix multiplication, great. That doesn't really add much. But this starts to work when you look at the higher and higher order terms. So if you look at the commutator between a 4th order tensor and a matrix, the exact result looks something like this. I don't know about you, but I don't look at that and immediately see any kind of structure. But if you write it in the graphical language, it becomes what I just said. It's the sum of all possible ways of connecting an up arrow from the first of these two objects with a down arrow from the second object. And then these are just tensor contractions. These are linear algebra operations. And in fact, these are things that computers are really, really good at doing. So now we don't need to work out all these big commutators by hand. We don't need to work out all these differential equations by hand. The problem has become a linear algebra problem, not a differential equation problem. And what's nice about this is that these tensors can be quite large, but tensor contractions can be massively parallelized. The previous version of this, I had a bunch of coupled ODEs. I don't know how to parallelize that in an efficient way. This, though, this I can. So if I have tensors that have hundreds, thousands, tens of thousands of elements in them, I can parallelize these multiplications really efficiently over multiple CPUs or multiple GPUs, which is where it works really, really well. So I can compute these things really quickly and efficiently. And I have some simple rules now, some simple building blocks that if I want to compute high order terms, if I want to include these sixth order terms or whatever, now I know how to do it. Now I just have a set of rules that I can give to the computer and I can compute anything I want. I can include the high order terms if I need to. I can compute the norm of them, the size of them. I can check if my approximations are accurate. Now we have a method here that works really well. And then just to motivate why GPUs work, this is a sort of benchmark from quite a few years ago, probably 2021 at this point, where I show you the time to diagonalize a system of size L on a CPU and a GPU, and you can see the larger the system size gets, the bigger the speed up you get from a GPU. Now, this was done on my own laptop years ago using some very old code just when we were starting out. We've not repeated these benchmarks recently. We probably should. I would expect the difference to be bigger. We can certainly get to larger system sizes. So all that to say, we now have a method that can diagonalize these Hamiltonians. We can do it efficiently, we can do it quickly, we can do it parallel, and we can go to higher and higher orders as needed. So this is the method we've been using now for a couple of years. This is the method that works. So let me show you a couple of examples of it in action and show you what we can compute with it. So if we come back to the interacting fermion Hamiltonian we looked at a minute ago, again, we've got our nearest neighbor hopping, we've got our repulsive interaction at the end, and we've got the disorder term at the beginning. Now, instead of making this completely randomly disordered, let me say I'm going to make it what's called a quasiperiodic potential. Now, again, maybe that's familiar to some of you, maybe it's not familiar to others. It has a kind of complicated looking form here, but where it comes from is essentially, if you imagine in ultra-cold atoms, if you take two counter-propagating laser beams that have wave vectors that are some incommensurate ratio of each other, and you superimpose these two beams, here you've got the green and the red, they're two perfectly ordered, perfectly periodic beams, but the resulting potential is the black thing. That looks pretty random. It's not like literally random because it's deterministic, it's built from two very ordered sine waves, but it looks kind of random. So it behaves a bit like a random system would, but it has some extra nice properties about it. In particular, if you switch the interactions off, this Hamiltonian has a phase transition at this W over J equals 2. So W is the disorder strength, J is the hopping. Now, if you had a completely random potential, there'd be no phase transition here. It would always be what you call the localized phase. In the quasi-periodic potential, you're allowed a delocalized phase at weak disorder, so a metallic phase, and an insulating phase at high disorder. So it's a bit more interesting than if it was purely random. It gives us some extra interesting physics. And what we were interested in is what happens to this phase transition as you switch the interactions on. Okay, what happens to it? Does it survive? Does it move? What happens? So you can run our procedure on this Hamiltonian, and then to leading order, you end up with a diagonal Hamiltonian that looks like this. I've just dropped the phrase L bits of that slide. Don't worry about that if you've never seen them before. This is the effective Hamiltonian that we end up with. And it's been known from the work of many people, I think Zachary yourself included, that these delta ij terms in the fixed point Hamiltonian, in random systems, they should decay exponentially with distance, right? So you've got this interaction term between a fermion at site I and a fermion at site J. This interaction should decay exponentially with distance. So one of the first things that we wanted to do with this method was just compute that, right? We've diagonalized the Hamiltonian, we've computed these deltas, let's compute the behavior of them with distance, and we fully expected to see that they will decay exponentially with distance. So I'm going to show you now the delta ij versus distance I minus j on a semi-log plot. So exponential decay should be a straight line. And I'll show you for a bunch of different values of disorder. They're color-coded. Do we get some nice straight lines? Sort of. We get this. So this is our log of the delta ij's versus distance. We'd expect some straight lines. If you squint a bit, maybe you can convince yourself there's some straight lines under there, but you're probably thinking they're not very convincing straight lines, really. And I would agree with you. So when I got this plot the first time, I thought, okay, disorder system, we need to run more disorder realizations, we need to do more averages, we'll clean up the data. No, they continue to look like this. So I thought, okay, maybe it's a finite size effect. Increase the system size. No, they continue to look like this. I went right back to the original differential equations code and ran that again. I got the same thing. And I was, at this point, starting to panic a little, thinking, okay, something has gone really, really wrong. Like, what is going wrong on lattice site 13 every single time? You know, why is there this like weird systematic dip? So I did. Any of you do numerics are probably familiar with that desperation where you just do Control F and start looking for errors because you know something's wrong, but you don't know where it is. So I thought I'm going to write down the position of all these weird dips, these weird deviations from straight lines, and just Control F, try and find out where in the code is the number 13 appearing and what's going wrong. So I wrote down the positions of all these dips. And if you'll let me have the first couple, they're hard to see, but they appear at distances 2, 3, 5, 8, 13, so on. So these are not random. These are the Fibonacci numbers. Where do they come from? Well, I kind of glossed over something on the last slide. I said this quasiperiodic system, you interfere two laser beams, the ratios of the wavelengths are some incommensurate number or some irrational number. The sort of standard thing you do in these systems is you pick the golden ratio. So if you pick the golden ratio for the potential, you get the Fibonacci numbers coming back in the diagonal Hamiltonian somewhere. And you can actually understand where this comes from. It's to do with resonances. It's to do with basically the potential is unusually correlated at certain distances. Because it's not random, it has these correlations built in. This structure is actually in the single particle wave functions too, but we didn't know about it at the time. And then just to check it, this was with the golden ratio, but there's a whole family of different metallic means. So you can compute the same thing for the golden ratio, and then for the silver and the bronze ratios, they have similar series of numbers associated with them. Instead of the Fibonacci numbers, they're called the Pell numbers, the Pell-Lucas numbers for the silver ratio. I forget the name for the bronze. And we find that actually we can predict where all these dips happen. And if you take a totally random potential, you get back the straight lines that we expected and that we thought we'd get in the first place. So this told us that the method, it did work. It was able to find something genuinely new, something that we didn't expect to find, something that we didn't know about. You might notice that in the bronze ratio, there's a couple of dips that I've not marked with dashed lines. We don't actually know where they're coming from. What we think this probably means is there's another sort of series approximation to the bronze ratio that is not known or that we haven't been able to find. So if the mood took you and you really wanted to, you could probably use this method to figure out another series approximation to the bronze ratio. Whether that's a good use of your time, I don't know, but in theory, you could do that. There are, yeah. So probably there's another ratio in there. The reason that there's two in the silver ratio is the silver ratio is something like 1 plus square root of 2. So you get the series approximation to the silver ratio itself, but then you also get the series approximation to square root of 2. So I imagine there's something like that happening in the golden ratio where there's a couple of different things happening that can all be approximated in different ways. But the point is, we can diagonalize the Hamiltonian, we can get some interesting behavior out of it. Cool, great.
Sorry, but just in the sense of the ratio here appears that's related to the phase.
So the ratio in the quasiperiodic potential here, we have this HI, W is the amplitude, phi is the irrational number that we use. And then the phase, we pick that randomly, it plays the role of a disorder realization. Yeah. So the phase is averaged over, phi here is fixed. And that's our golden ratio or silver ratio or bronze. And yeah, we can get it to work in every case. So method works, we can diagonalize the Hamiltonian. Cool. This was in one
diagonalizing like in the like n particle.
Yes.
Like many body.
Yes. Quite what you call the Hilbert space, I don't know, but you're diagonalizing it to look like this top line here. So we never build the thing as like a big exponentially large matrix, right? We're trying to diagonalize it
Right, you're just getting the couple of
Right, exactly, right. Yeah, it's almost like the way I think about it is that we're doing it in a sort of an algebraic analytical way where you write down the couplings at every order and numerically we obtain the couplings, but we don't ever build the Hamiltonian as a matrix acting in Hilbert space. So quite how you choose to look at this is kind of up to you. I've got a PhD student who sees this in a very, very different way than I do because he really cares about the Hilbert space that it acts in.
Yeah.
So depending on your perspective and your background, you might have a different take on what exactly this does. But to me, I want the Hamiltonian to have this kind of operator form, and I'm numerically computing the coupling. Cool. Right. So that was all in one dimension. The extension to 2D is actually pretty simple. So a 2D system can always be mapped onto a 1D system by just unfolding it. So you can imagine taking your 2D grids and just stretching it out into a big 1D system. If you do this, the nearest neighbor couplings in the 2D system, these orange lines, become long-range couplings in the 1D system. But our method can handle long-range couplings. That's not a problem. In fact, our method generates long-range couplings at intermediate stages anyway, so you might as well start with them built in the first place. Why not? It doesn't cost you anything. So we can handle long-range systems. That means we can handle 2D systems and actually small 3D systems as well. We've done both. So we can do 1D, we can do 2D, we can do 3D. You might have noticed that at no point did I talk about dimensionality before, and that's because the complexity of this method scales with the number of lattice sites. It doesn't actually care where you put the lattice sites in space. So 100 sites in 1D has the same complexity as a 10 by 10 grid in 2D, and whatever the closest equivalent of that would be in 3D. So total number of lattice sites that matters, not the geometry. We can have 2D systems, we can lay them out in interesting patterns. You can look at Kagome lattices, square lattices, triangle lattices, take your pick. So that stuff we kind of get for free, which is nice. So we can handle 2D systems. The last...
that you choose to go through your 2D lattice?
The final Hamiltonian will depend on the mapping, yes. So you could imagine doing this in a different way, but the overall complexity doesn't. So you'll end up with slightly different long-range couplings if you do the mapping in a different way. Yeah, I guess the details of the flow will change, but the overall complexity will not change.
Sure, just regarding the thing I asked before, so at the end, how many eigenvalues do you actually get?
So we don't get the eigenvalues themselves, right? We just have an expression for the Hamiltonian in terms of...
The HIs, oh, I guess no, but you also have these other terms.
Right. So in the non-interacting case, the HIs were directly the eigenvalues. Okay. I was a little bit fast with that. In the interacting case, in the diagonal basis here, we know that the eigenstates are all just product states, right? They're all possible combinations of zeros and ones. So given any eigenstate in the diagonal basis, you can apply this Hamiltonian to it. You can compute its expectation value. So you can compute the eigenvalue of any eigenstate.
Construct them all kind of from this if you wanted to.
If you really wanted to.
They'd be the same number.
Yeah, exactly. Yeah. So it's probably not great as a ground state search method, but you could do it if you wanted to. So you have access to all the eigenvalues with this method though. And that kind of brings me on to the last missing ingredient.
This in principle,
So that I don't know. We've looked and we've never been able to find it because I don't think you can get it at this order. You must get it if you include all the terms to infinite order.
Yeah.
But at, what point do you need to go to in order to get it? That we don't know. At this order, we've never found it. So at that point, we kind of gave up looking.
yeah, because this will generate some polynomial.
Exactly. Yeah.
Combinations.
We kind of hope that we might see signs of it. We might, deviate from Poisson level spacing and see something, maybe not proper level repulsion, but see something at phase transitions. But in fact, we don't. It seems to always be Poisson. In theory, we can include the higher order terms. Eventually, we'll find it, but I don't know what eventually means. So we haven't tried looking for it because my suspicion is probably we need to go to quite high orders to see that.
But what about, for instance, applying it to this problem?
We can do that. Yeah, we can do that. But if it's a non-interacting system, you can get level repulsion. We've checked that, so that works fine. Yeah.
Yeah, that one will have.
Yeah. You can also do 1D with power law interactions, power law hoppings, rather. There's also a phase transition there. That one we did check, and we do get level repulsion. So non-interacting systems are exact and everything works. Interacting ones, we've made an approximation. that approximation so far seems to be throwing away level repulsion. Theory, it'd be nice to add it back in, and then we can start looking for phase transitions, because there is no visible phase transition in these either, which is part of the reason we were looking at these. We're hoping that there would be a clear distinction between a flat behavior in the delocalized phase and some decay in the localized. Yeah, so we never, you can see there's a trend, but there's no clear transition in there. So it's an approximation. As I say, we can include the higher order systematically. So if there's something we really want to compute, we can add them back in and we can look for it, but there's no guarantee that we're going to find it. So if you need exponential accuracy, probably you need a lot higher order terms. And for level spacing, I think we need that. Cool. So question over there?
It's
I imagine it would be a straight line. So if you do that, then it's no longer quasiperiodic. It's going to have a lot of structure built into it, and you're going to have a lot of resonances and a lot of correlations. You're not going to see the dips for sure. I don't know what you would see, because I think that wouldn't be a localized system. So I think that's kind of kicking up against the boundaries of where this starts to break down. So I think you'd probably get a straight this order, but I don't know how bad an approximation would be. Okay, yeah, one more.
So what is the actual complexity of the method? Like, it has to be exponential in some the number of.
Well, no, so here it's polynomial because we're making an approximation, right? Because we're throwing away these higher order terms. So you could say that to store this, the highest order term here, Ni and J, that's got 4 fermion operators, C dagger I, Ci, C dagger J, Cj. So our sort of tensor that we store that in has entered the 4 elements. The highest order tensor contraction we do has either entered the 5 or entered the 6, I don't remember which is quite a lot, but as I say, we can parallelize that quite efficiently. So the limiting factor there is not the number of computations we need to do, it's memory on GPUs. So we did the original studies of this with 12 gigabyte GPUs. We've now got 48 gig GPUs in Edinburgh, and we're buying a 96 gigabyte GPU soon. So we should be able to do better than what we've done here, just on brute force computational improvements. But yes, everything is polynomial, but it is approximate. Cool. All right, so the last thing I wanted to say was the missing link between what you've seen so far and what I showed you at the beginning, the time evolution. So there's a question down the front about eigenvalues. We've got the eigenvalues, and the cool thing about this is that we can now compute non-equilibrium dynamics. That's a really good use of knowing all the eigenvalues. So rather than trying to compute the eigenstates, let's compute dynamics. So visually speaking, let's say I have some operator and I want to time evolve it. Now, if I knew how to do this exactly, I could do it exactly. I start from the operator at time 0 over there on the left, I time evolve exactly, and I get a time evolved operator. Brilliant. In general, we don't know how to do that. So the sort of scheme with flow equations is we do this unitary transform. We diagonalize the Hamiltonian. So we move it to this L to infinity basis where each tilde is some diagonal Hamiltonian. And then we transform the number operator in the same way. Now we've worked out the transform in diagonalizing the Hamiltonian. We can transform the number operator to be in the same basis. No problem there. Now the Hamiltonian is diagonal. Time evolution is just multiplication by phase, right? We can exponentiate a diagonal Hamiltonian. Great, that's easy. And then you get a time evolved number operator in this diagonal basis. That's not always the most convenient thing. Ideally, we want it back in the original basis. So then you have to undo the unitary transform to get back to the time evolved operator in the original basis. So this is the steps that you go through. It's a little bit convoluted, but that's the price you pay. If you can't do it exactly, you have to go around this lengthy route. Now, there are a couple of nice features about this. One is time evolution at the top, multiplication by phase. I don't need to go through short times to get to long times. I don't need trotter steps. I don't need a DT. I can go straight to the long time limit if I want. Even analytically, in fact, you can go straight to the long time limit. So that's really, really nice. Also, we don't time evolve states here because that's actually quite hard. But if you time evolve the operator, you can apply it to a bunch of different initial states effectively for free, which is quite nice. The downside is that you have to invert this unitary transform for every time that you look at. That can get quite expensive, but you can do it. So here, I'll just very briefly show you some results. These are from disordered spinless fermionic Hamiltonians. I'll not tell you much about what these are. You can check the papers. The point is you can compute the dynamics here on the left of number operators, and on the right, this is the imbalance. It's like the sum of number operators across the whole system with an alternating sign. You can do this. Bear in mind, every single dot that you see here is the result of me inverting a unitary transform, which is quite expensive. And then you have to average them over hundreds of disorder realizations. So you can do this, but computationally, it becomes quite expensive. So one other thing that we can do with it that is quite nice is that we can look for quantities that don't require reversing this unitary transform. And in particular, any observable that involves a trace over basis states, you can compute that trace in any basis. So you can compute that in the diagonal basis, where we know all the eigenstates, we know all the eigenvalues. If you can compute it in any basis, we might as well just do it there and not have to reverse the transform. So in particular, for things like infinite temperature correlation functions that look like this, you have a trace over basis states. Here you have a sum over I, where you sum over different eigenstates. If you can transform everything here into the diagonal basis, you can compute that in the diagonal basis, and ultimately that's what we end up doing. So you can pick the states to be in the diagonal basis, you can transform the operators using the thing I just showed you, and that gives you back this result that I showed you right at the beginning. So these are infinite temperature correlation functions. They are the trace of some operator across all the eigenstates in the basis. We can compute them in 1D if we like. We can compute them in 2D at essentially no extra cost. And we can compute the times to basically as long a time as we like, because we don't have to go through small Trotter steps. We can just go straight to long times. You also note in some of these plots, there are these black dashed lines. These are actually the long time limits. So from the transformed operator, you can directly get a long time limit and check that they match the numerical results. And for strong disorder, they do. For weak disorder, some approximations break down. But yeah, qualitatively, it all works really, really well. So we've come full circle. We've come back to the thing I showed you at the beginning. This method allows us to simulate the dynamics of extremely large systems in 1D, also in 2D. I've not shown you 3, but we have some results on 3. You can do 3 if you like. It allows us to simulate very, very long times, and it allows us to simulate quite challenging things like infinite temperature correlators, which are quite difficult to do actually with tensor networks. So we can do a lot with them.
What is this D one?
Oh, that's the disorder strength. Sorry, we're running out of time, so I'm being a bit quick at the end. So these are disorder strengths. Yeah, so weak disorder, what you see is the infinite temperature correlator goes to 0. What that tells you is the system effectively has no memory of its initial state. Strong disorder, the infinite temperature correlator remains non-zero. The system, in some sense, remembers the initial state. So this is used as a diagnostic of thermalization and localization. If your system thermalizes, this thing goes to 0 at long times. If it does not thermalize, it remains not 0.
And these peaks on the right of the data peaks, the rational.
No, they're just noise, I think, from disorder realizations.
I think they seem very converged.
Yeah. Yeah, I don't know where they come from. I'm not sure exactly where they come from, to be honest with you. They do also appear in exact data for small system sizes, so I don't know. The timescales there are relatively short, so essentially for short times, you're just looking at dynamics of a non-interacting system before the interactions really kick in. So I don't really know where they come from. There is a version of this plot that has exact diagonalization curves plotted on top for very small lattices, and we can show that it all agrees, but there's so many lines on that I didn't want to include it here because it's a bit of a mess. So yeah, that was kind of the punchline. So let me just pop a summary up because I think we're a little over time and I'm aware people might need to leave. So summary is flow equations I hope I've convinced you they're a pretty powerful technique for simulating interacting quantum systems. I've said here they're non-perturbative. I haven't really gotten to why they're non-perturbative. They are. You can add in additional corrections to make them even more accurate. Originally, they were limited to strongly disordered systems. They now work for clean systems. We can get to very large system sizes, very long timescales. Next things we're doing, everything I've done so far was kind of done in the dumbest possible way. I didn't really make use of any symmetries, the fact that anything is unitary or Hermitian. So it's kind of inefficient. The fact that we can already go to these system sizes is kind of amazing to me. There are a lot of efficiency improvements we can make using symmetries and things. We have some ideas about how to distribute this across multiple nodes and multiple GPUs to get over the memory limitations. And there are some proposals to use similar methods on quantum computers. So that's something that two of my students are looking into, whether we can do some kind of hybrid quantum computing method. I've talked so far about spinless fermions. We have looked at spinful fermions, the Hubbard model as well, but you can do a whole bunch of other things to it. We've looked at Flaquet models. One of my students right now is looking into open systems, so applying this method to Lindblad master equations. You can apply this to bosons. It literally is just Control F, remove all the minus signs that pop up in the tensor contractions. We haven't done this yet, but we can. We looked into Majoranids at one point, but the time crystal people scared us, so we stopped. And there's other things like lattice gauge theories that we're really interested in, maybe some spin glasses. Pop up a bunch of relevant references here in case anyone's interested. And because we've gone a bit over time, I think I will stop there. Thank you.